Hello everyone, welcome back. This is Dr. Giuliano. In this video, we're going to be talking about sample size. So the first question is, what is sample size? And this is the minimum number of patients needed to meet the primary outcome of a study. And the next question is, well, why do we need to calculate sample size? And this is really for two reasons. The first being to minimize type 2 error. Because remember, we're not going to be able to completely avoid type 2 error from occurring, but we can try to minimize it by increasing our sample size. And the other is to limit patient exposure to a harmful substance like a drug. So there's no point in enrolling tons and tons more patients if you're not going to get any additional information out of that. Which brings us to our first objective, which is describe the important factors used in calculating sample size. And after I go over these, we're actually going to do some practice calculations using a free online sample size calculator. So you'll need to understand what each of these components actually mean. And there's a few things we'll need to determine first. And the first thing we'll need to do is determine the study design. So is it a randomized control trial? Is it a cohort study? Is it a case control study? The next thing we'll need to determine is how many groups are there within the study. So if we're looking at a drug versus placebo, that's going to be 2 groups. Next, we need to find the primary endpoint, and we need to look at the type of data that the primary endpoint is using. So what type of data is primary endpoint using? And that could be either nominal, ordinal, or continuous type data. And following that, what statistical test is being used. And this is going to correlate, of course, with the type of data. We'll talk more about statistical tests later on, so don't stress over this part right now. I'll walk you through that as we go through some of the examples. Next, you'll need to identify the alpha that is set within the methods. Remember, this is usually going to be 0.05 or less. The alpha is actually used in calculating the sample size itself. The smaller the alpha, the more patients are needed. So smaller alpha equals more patients, or you'll need a larger sample size. Next, you're going to want to identify the beta in the methods. Remember, beta refers to type 2 error and alpha refers to type 1 error. Beta is usually going to be 0.2 or less. And the calculator sometimes will ask for power. Remember, power is calculated by 1 minus beta equals power. So if the beta is 0.2, 1 minus 0.2 would be a 0.8 or 80% power. Usually our power is going to be 80% or greater. Smaller beta also means you'll need more patients. The next part of the calculation is identifying the clinical difference that the authors are looking for. The authors choose this number by identifying what the minimum difference in outcome between treatment and placebo would be clinically. So you need to make sure that you agree with what they think the minimum clinical difference is. So you'll be looking for the minimum clinical difference, and this should be established by the authors. There's no black and white rule here. You'll have to look at what the outcome is and then the percent difference. So for example, if we're looking at mortality, a 2% difference in mortality might be really important, but a 2% difference in triglycerides may not be as important. So you need to sort of take the outcome and the percentage into account and think about clinical practice and if it's important or not. So for example, authors will commonly have a statement like this. We expect the control group will have 15% hypoglycemia or low blood sugars, and the treatment group will have 10% hypoglycemia. So they're seeing an absolute percent difference here of 5%, and they deem that this is the minimal clinical difference they think is important. This is going to be used in calculating how many patients you need. The smaller the difference, the more patients you will need. Because it's much harder to find a needle in a haystack, I think is the best example. If something has a huge difference, you're going to easily notice it with a lot less patience. Something you'll see when reading about sample size is something called the effect size. The effect size is a relationship between the mean, which could be the minimum clinical difference, and then the standard deviation. Which comes to our next thing that you need to look for, and that is variability. So you need to identify set variability, and this is really going to be done if the type of data is continuous and there's a mean, and then the variability is going to be the standard deviation. Authors will find this by evaluating previous literature, or they might use preliminary data, or they might make an educated guess to come up with a standard deviation. But they should have this information within the methods section of the paper. So now that we talked about each of the components that you're going to need when calculating the sample size, let's do a few examples. Which brings us to our second objective, is to appraise the sample size calculation in a journal article using a sample size calculator. And I will put the link up for the one that we'll be using. So this is the link. It's a free calculator from Vanderbilt. So you can follow the link and download it there. So I will go ahead and pull it up. So I have our first example, a study looking at chlorothalidone versus hydrochlorothiazide and the management of blood pressure. And the first author's name is Ernst. This is a paragraph out of the methods portion. I want you to see how this is normally worded. And the way that they word it, this is a priori calculation, which means it was done before the study was conducted, suggested that a sample size of 20 should give a power of 0.8. Remember, that's 80% power to detect a difference in a mean change. That's the minimal clinical difference right there of 4 millimeters of mercury, looking at systolic blood pressure, between the two treatments using a paired t-test at the 0.05 significance level. So you see the statistical test there, and then the 0.05 is the alpha. Assuming a standard deviation, so there's the variability because systolic blood pressure is continuous type data, and the standard deviation of 6. And then they also talk about something called oversampling, and that simply means just enrolling extra patients just in case patients drop out or they're not compliant or something of that nature. So let's see if we can get similar results using the sample size calculator. So on here we see that they used a t-test. So we'll go to t-test on here. T-test is a very commonly used statistical test. So we see here that they say the data was paired because this was a crossover study where the patients served as their own control. So we need to make sure we choose paired here, and we do want to make sure we're outputting to sample size. They set their alpha at 0.05. The delta here is the difference between population means, and they were looking for a difference of 4 between their population means, and they had a standard deviation of 6, and their power was 0.8. So now we have all the information in there for the t-test. So we'll go ahead and hit calculate, and it gives you a nice little paragraph down here, but if you look up here where the output area is, it shows that our sample size is 20. Well, that is exactly what they calculated within their study, so we can see that their calculation was accurate. And if we do 20 times 20%, that is equal to 4, so they added 4 patients on in case dropout occurred, and realized that is 20 patients in both groups. So let's move on to our next example. Now our next example is from the Nice Sugar study. This was a large randomized controlled trial that was looking at blood sugars within the hospital, and they actually increased their sample size partway through based off another study that had been published that showed a little bit lower percentages of the event they were looking for, which was mortality. So they decided to partway through to redo their calculation. Now they increased their sample size to 6,100, and that was with a 90% power to detect a difference in mortality. They were looking at mortality, which is a yes or no outcome. So this is going to be a type of nominal data. So with nominal data, you look at the proportion difference between groups, and they were looking for an absolute difference in mortality of 3.8%, and that was assuming a baseline mortality of 30%. And then again, that alpha is less than 0.05. And we see here they were using the chi-squared test. So there are a lot of ways to say nominal in statistics, and another way of saying that is dichotomous. And we can go up here and click on dichotomous, and you see that you can click on power or sample size again here. We see here that, so we clicked on sample size. Then in this study, it was not a paired study. They were 2 separate groups, so it's not matched or paired. This is independent. This is a prospective study, and they're talking about proportions here when they're talking about the outcome of the study. And they didn't use Fisher's exact test that's usually used for smaller groups, they used the chi-squared test. And you can see they even said they used the unadjusted chi-squared test there. The alpha was set at 0.05. The power was set at 0.9. This is the probability of the outcome in the control group, which was 30%, as you see there. And then this next one here is the probability within the treatment group. So I took 30 minus 3.8%, and that was that probability there. And then this is the ratio of cases to controls, and they did a 1-to-1 case to control ratio. And then we can go ahead and hit calculate, and we'll see what number we get. So we got a number of 2,939. Remember, we'll want to multiply that by 2. So let's do that math. And 2,939 times 2 is equal to 5,878. Now, in this case, it doesn't match up exactly to that number of 6,100. I'm guessing what they did, they also accounted for some patients being lost within their study because they were following them for 90 days. So I'm guessing they had made some adjustment there, but they didn't necessarily say that in the methods. So should we be worried that our number didn't match up to their number? Not necessarily, because their number is actually larger than our number was. So they said they needed more patients to achieve that 90% power. However, if their number was less than our calculated number, then we should start to be worried, because then there might be a higher chance for type 2 error to occur. I hope these examples helped. The next videos will start to go into the statistics portion of a journal article.